At the moment, I'm building up a CORDIC unit. Now, I've already created a full course on the CORDIC algorithm, but the course was created a couple of years ago, so I'm having to go over and remind myself exactly how the algorithm works. But I've made a start on it, and I've got a tiny little bit of functionality built up, and what I intend to do is try and get that finished over the next few weeks, and then add it into the floating point unit, and then build up a more detailed mathematics library which we can use going forward. So that's what I am doing at the moment. Now, one little thing, I did note that whenever I generated my division and square root, I used the fast inverse square root algorithm. Now, I really used that because it was just an interesting thing for us to do, okay, and it was an interesting way for us to work to create the division and the square root. But the fast inverse square root algorithm is an approximation, and whenever the values get to very, very low values, so for example into subnormal numbers, it starts to, the accuracy starts to kind of disappear a bit. So what I did was I worked out a point at which the accuracy was dropping off, and that was a point roundabout for numbers of the form 00E5. Okay, so that's just getting in the subnormal range. So it turns out then for E5 down it had very low accuracy. So what I did was I generated a lookup table for those 229 values all the way down to 00, and the lookup table is in here. So this is the fast inverse square root section, and what we really do is whenever it gets down below a number E5, so this is a test, a comparator to test whether the number is below E5, so E4 and below, then it misses out the fast inverse square root architecture here, and it just goes straight into a ROM. And I've generated the 229 values for the square root of these numbers. Okay, in fact I didn't generate it, I got ChatGPT to generate the values for me. Now you have to be careful because ChatGPT sometimes gets it wrong, but I'm going to monitor that and I'll check it out and see whether the values are in fact correct. So I've put all the values into a ROM. It will miss out the fast inverse square root algorithm, and it'll just jump straight in and it'll give us the square root value. Of course, you could look at this and say, well, you could have just missed out the fast inverse square root algorithm altogether and just had a full ROM based architecture where you just went in and just picked out the square root of all of the 64,000 or 65,000 possible values, so it'd be 2 to the power of 16. Now you could potentially do that, okay, but it's not a route that I wanted to go down. First of all, I wanted to do the fast inverse square root algorithm because it was interesting, okay, and it was a different approach for us to take. So that's really why I've decided to go down that path. So in this instance here, the fast inverse square root algorithm gets missed out and we just go through the ROM. Now the same occurs for the division. So in the division section, you go to the floating point unit, and we've got the division section here. Okay, just ignore all the red wires. They're just red for the moment because I've not set it up in order to run a simulation. Okay, so in the fast inverse square root, again, we're going to use the we're still going to use the, for the division, we're still going to use the fast inverse square root algorithm, but again, for values that are between 0 and E4, we're going to work out the 1 upon the root of that value in a lookup table, as opposed to using the actual algorithm here. So we've got, again, this lookup table here, which now generates 1 upon the square root of these numbers, and it bypasses this fast inverse square root algorithm for well, it bypasses the generation of the magic number, okay, if you like, and it will generate the 1 upon the square root directly from here, as opposed to within this block here. Okay, so that means that it's great for us because there's only, say, 229 values where the values kind of went off a bit. So it's quite easy for us to go ahead and generate this. And now I've ran the simulation, and the simulations run really quite quickly. There's not any problems. There aren't any, it doesn't stop and start at all. So I'm quite pleased that the floating point unit runs quite well. Also, I've worked in all of the edge conditions and generated all of the proper flags here. So we've got the not a number, plus infinity, minus infinity, and 0. Okay, so the edge conditions have been checked out as well. One other thing is that the floating point, what's the right word? The instructions for the floating point, we've got 24 different floating point instructions. Okay, so I think there are 20 different floating point instructions at the moment, and the reason why we've got 20 is because we've got 5 different things that we can do. So we can do add, subtract, multiply, divide, and square root, but we've also got the addressing modes for each of those. So there's 4 addressing modes for each of those mathematical functions. Okay, so we end up with a 5 times 4, which is 20 different instructions that we have now got. Of course, we will add to those whenever we add in the CORDIC algorithm. So I can only show you a tiny bit of where I've got. So let me just bring this up for the moment. I think if I might just have it handy here. Open CORDIC 1. Okay, so I've not got very far, as you can see. I was just sitting on the floating point unit here, and oh, that's my image disappeared, I believe. Okay, so I've got the floating point unit sitting in here. I'll get my image back up again. Okay, I think there's something strange with the camera. It cuts out every so often. So every 10 or so minutes, the Canon camera cuts out. I have to change one of the settings in it. I've got some of the numbers that we require here, and we're going to start off with an initialization. So there's very little built, but I'm starting to kind of put it together just now. But right now I'm in that sort of strange position where I've created the mathematical course describing all of the mathematics, but I've kind of forgotten it, and I have to go and have a look and see how it all works again. And right now my brain's kind of like a little bit fuzzy and a little bit empty, and I need to try and get in my head exactly how I'm going to create this architecture. And I've decided, rather than just creating 1 or 2 functions like the sine or a cosine, I want to try and regenerate every function which I've shown within the CORDIC algorithm course. So that's my intention, and that's what I'm trying to do at the moment. Okay, so that's where I am, and I am continuing. And I know it's a long exercise, especially since I've not been doing an awful lot over the last few months, but things are picking up a little bit, and my interest and my enthusiasm has been rekindled somewhat over Christmas. So that's all for this video. Continue watching. I will be continuing making the videos, and as I said, I tend to work in fits and starts, so you might not get many videos for a little while, and then you'll get a whole load all at once. That just tends to be the way I work. So a happy new year to everyone, and it's been a good start. I've been busy over the last couple of days, and long may that continue for the rest of the year. Thank you for listening. I'll get you on the next video. Goodbye.